Hi, I'm Vedant, an engineer on Apple Vision Pro. In this session, I'll be showing you how to build compelling experiences with spatial photos and spatial videos. It's been a year since we announced spatial photos and videos, a new medium unlocking a whole new dimension to visual storytelling, and we've been amazed by how people are using it to relive personal moments with family, share stories from around the world, transport us underwater and into the air, and so much more. And now, with machine learning, any photo can be converted into a spatial photo, allowing you to relive old memories in a brand new way. Today, I'll be showing you how you can add spatial media experiences to your own apps. First, we'll take a look at the different types of stereoscopic video experiences available to understand what makes spatial so special. Then, we'll take a tour of all the new spatial media APIs and the capabilities they enable. Finally, for the power users who want to create custom spatial media, we'll take a deep dive into the spatial media formats. Let's start by looking at the different types of stereo video. Stereoscopy is a great way to enhance video for Vision Pro, and Apple offers several formats that support it. First, there's 3D video, like the 3D movies available in the Apple TV and Disney Plus apps. These render on a flat screen, but since the content is stereoscopic, it has depth. Moments in the video can appear to pop out of the screen, or recede into it. Then there's spatial video that you can capture on Vision Pro and iPhone 15 Pro. It renders through a window, with the faint glow around the edges and custom playback controls. This enhances the sense of depth and softens some common sources of discomfort. Spatial video is great as a point-and-shoot format. People can shoot comfortable, compelling content on devices like iPhone without needing to be an expert in the rules of 3D filmmaking. For high-end professional content, there's Apple Immersive Video, shot in 180-degree 8K resolution with spatial audio. In visionOS 2.0, this now comes with a preview presentation that, like spatial videos, renders content through a smaller floating window. This lets people watch their videos in stereo while still being able to interact with other apps. Each of these experiences looks great like this, but they really shine in full immersion, where other apps get backgrounded and the content takes focus. They each have their own flavor of displaying in full immersion. 3D video docks into an environment where the screen moves backwards and enlarges. This is my favorite way to watch movies, both 2D and 3D. To learn how to add docking to your own apps, check out the video titled Enhance Video Playback and Immersion in Your Custom App Environment. Spatial video expands into its immersive presentation, where the content is scaled to match the real size of objects. The edge of the frame disappears, and the content blends seamlessly into the real world, so it feels like you're in the content, not just looking at it. People can fully immerse themselves in a spatial video by tapping the Immersive button in the top right corner, and collapse it with the Exit button at the bottom. This allows them to return to a windowed presentation that allows multitasking with other apps in the shared space. For Apple Immersive Video, the video expands into its native experience. The video screen wraps around the viewer, and pass-through is disabled altogether, putting you right inside the action. This unlocks new possibilities for professional creative storytelling, where the viewer can be transported into the story in the highest possible fidelity. Together, 3D video, spatial video, and Apple Immersive Video create a rich ecosystem of stereoscopic content, each well-suited to different contexts. And these are just some of the stereo media experiences available on visionOS. There's also spatial photos, which use the same portal and immersive presentations as spatial video, custom video experiences that you can build with APIs in AV Foundation and RealityKit, and the same way photos and videos are enhanced with stereoscopy, real-time 3D content can also look amazing in stereo, especially when that content is interactive. For more details on how to achieve that, check out the video, Bring Your iOS or iPadOS Game to visionOS. Now that we know what spatial media is, let's see how we can add them to our apps. In this section, we'll go over 3 new areas of APIs: recording spatial videos, detecting if a file is spatial and loading it, and different options for presenting it on visionOS. You'll notice throughout this section that there's no new framework for spatial media. That's because it's all been integrated into the existing Apple frameworks you already know and love: AV Foundation, PhotoKit, QuickLook, WebKit, and more. With just a few lines of code, you can add spatial media to your apps the same way you would for other types of media. First, I'll look at how spatial video gets recorded. On the iPhone 15 Pro, we made the enabling change to put the wide and ultra-wide cameras side by side, instead of diagonally. This means that when the phone is held in the landscape orientation, the 2 cameras are on the same horizontal baseline, oriented just like human eyes are. This is what enabled spatial video in the Camera app. and we're now making that API public, so any app can record spatial video. Let's see how. We'll write some code to record normal 2D video, then extend it for spatial. With AV Capture, we'll be using the following data flow. We first need a device input that represents input from a capture device, like a camera. We then need a movie file output that manages the output and writes it to disk. The input and output are connected with an AV Capture connection, and an AV Capture session coordinates the data flow between these components. Let's write that out in code. We first create an AV Capture session, then create an AV Capture device, setting it to the default system preferred camera for now. Then, we add an input to the session, add an output to the session, commit the configuration, and start running it. If you've used the camera capture APIs before, this flow should look extremely familiar to you. If you haven't, I'd recommend checking out the AVCam sample code project on developer.apple.com. Now, let's extend this code to record spatial video. We just have to do 3 things: change the AV Capture device, pick a supported video format, and enable spatial video recording on the output. First, we'll change the AV Capture device. We'll use the built-in dual-wide camera since spatial video requires the wide and ultra-wide cameras to be streaming simultaneously. Next, we'll pick a video format that supports spatial video. We iterate through the formats in the video device, checking if "is spatial video capture supported" is true. When we find one for which it is, we make it the active format on the video device. Let's make sure to lock and unlock the video device appropriately, and let's add some error handling. We'll return false if we don't find any spatial formats that meet the criteria. Finally, let's check that spatial video capture is supported, and when it is, set "is spatial video capture enabled" to true. Note that this only works on iPhone 15 Pro, and "is spatial video capture supported" will return false for other devices. In that case, you'll need to handle that error appropriately. And that's it. With just those 3 small changes, we're all set to record spatial video. All of the complexity of synchronization, camera calibration, encoding, and metadata writing are abstracted away. You just get a fully formed spatial video file on disk from the movie file output. And while it really is that easy, there's 2 more things we can add to get even better quality recordings: improved video stabilization and a great preview. Let's see how we can do that. To get the best quality stabilization, set the preferred video stabilization mode to Cinematic Extended Enhanced. This uses a longer look-ahead window and crops more of the frame to get even smoother videos. Smooth video is always desirable, but it's especially important on visionOS since the screen sizes can be made much larger than other devices. You can get a video preview feed with the AV Capture Video Preview Layer API, the same way you would for other video formats. However, since the iPhone displays monocular, we can't give you a spatial preview, so it always shows the wide camera, regardless of device orientation. It's important to note that the 2 cameras used for spatial video, the wide and the ultra-wide, are actually different kinds of cameras. The wide is the best camera on iPhone for general photography, and the ultra-wide is optimized for dramatic wide-angle shots and close-up focus. The 2 cameras each have different light-gathering abilities and minimum focus distances. When shooting spatial, most of the time these differences aren't too noticeable, thanks to the computational photography techniques we use to correct them. However, when shooting spatial videos in low light, the noise levels in each camera might be different, causing discomfort when viewed in Vision Pro. Similarly, shooting a subject closer than one of the camera's minimum focus distances can also cause a focus mismatch, which can be uncomfortable. Since the iPhone preview is monocular, you might not notice these issues until you view the videos later on Vision Pro, and by then, the moment you were trying to capture might have passed, and it's too late to re-record it. To address this problem, we created a new Spatial Capture Discomfort Reasons variable on AV Capture device. You can observe this in your app with key value observation, and render appropriate guidance UI when the subject too close or not enough light conditions are detected. Here's the iPhone camera app surfacing warnings when I get too close to my subject, and dismissing them when I move back. We recommend that you show some similar guidance UI in your apps. Now that we've recorded some spatial video, let's see how we can play it back. The first step is to detect that an asset is spatial and load it. And there's a few different ways to do that: Photos Picker, PhotoKit, and AV Asset Playback Assistant. The Photos Picker API presents a view that helps users choose assets from their photo library. It now supports filtering on spatial assets. Specify .spatialMedia in the matching parameter, and it'll filter the user's library to only show them their spatial photos and videos. If you don't need input from the user, you can use PhotoKit to programmatically fetch all spatial assets from the user's photo library. Just set spatial media as your PH asset media subtype when constructing your fetch predicate. We can also modify the fetch request to only return spatial photos, or only return spatial videos. And for video, you can also use AV Asset Playback Assistant. Its playback configuration options can be queried to check if a local asset is spatial. This is a great option if your app loads videos from sources outside of the photo library. Now that we can load our spatial content, let's present it. Again, there's a few different options to do this. There's the Preview Application API in the QuickLook framework that supports photos and videos, the Element Fullscreen API in JavaScript that supports loading spatial photos from the web, and AV Player View Controller in AVKit that supports spatial video. QuickLook is the system standard way to quickly open files on visionOS. With the new Preview Application API, you can now spawn a QuickLook scene from inside your own app that hosts your own content. It supports both spatial photos and videos and uses the full spatial presentation, just like the Photos app. For more information about the Preview Application API, check out the video, What's New in QuickLook for Spatial Computing. Then, there's the Element Fullscreen API in JavaScript, which allows spatial photos to be opened from a web page in Safari. Like Preview Application, this opens in a new scene and comes with the full spatial presentation. To learn more about the Fullscreen API, check out the video, Optimized for the Spatial Web. Finally, there's AV Player View Controller, our cross-platform API for playing all types of video content. It supports both 2D and 3D video, and so it's a great option when you want to display both types of content with a consistent presentation style. It also supports HTTP live streaming for spatial video. There are a few things to keep in mind when using AV Player View Controller with spatial video. The video only displays in 3D when it becomes full screen. In the inline presentation, it'll display as 2D. The easiest way to make content full screen is to size the AV Player View Controller to match the frame of the window scene. Note that even in full screen, AV Player View Controller will use the 3D video presentation, not the spatial one. Since spatial videos are built on top of MVHEVC, they're also valid as 3D videos, which is how AV Player View Controller will treat them. If your app needs the full spatial presentation, use Preview Application instead. Finally, as you design your apps, try to minimize the amount of UI placed directly on top of the video. Uncluttered UI keeps the focus on the content and minimizes the risk of depth conflicts. We've now seen multiple ways to record, detect, load, and present spatial media. As an app developer, the APIs we just saw are all you need to get started using spatial media in your apps. But for those who want to create custom spatial media, let's take a look under the hood. At a file format level, a spatial video is a stereo MVHEVC video with extra spatial metadata. And a spatial photo is a stereo heat with two images in a stereo group, along with some spatial metadata. To understand how to read and write these files, we have two sample code projects and an article on developer.apple.com. Now, let's take a deeper look at that spatial metadata common to both file formats. Spatial metadata comprises of a few things. There's the projection, that defines the relationship between objects in the world and pixels in the image. Spatial photos and videos always use the rectilinear projection. Then there's the baseline and field of view. These describe physical properties of the camera that captured the spatial asset. And there's the disparity adjustment, which controls the 3D effect in the windowed presentation. Additionally, there are some guidelines for how the left and right images should be created. Since these are image characteristics stored as pixels in the image, they're not explicitly metadata fields, and aren't enforced when checking if a file is spatial. However, they're still important to understand and get right for the optimal viewing experience. For optimal image characteristics, the left and right images should be stereo rectified, have optical axis alignment, and have no vertical disparity. That's a lot of new technical terms. To understand them better, let's see an example. Here's Howie, the hummingbird, who'll be the model for our spatial photo shoot. To capture him, I've got two cameras in a stereo pair, aligned horizontally. They each take a synchronized picture that form the left and right images of our stereo pair. These are pinhole cameras, so the images are rectilinear, meaning that straight lines in the world appear straight in the images. Our first metadata field is the baseline, sometimes called the interaxial distance. defines the horizontal distance between the centers of the two cameras. The optimal distance to set the baseline depends on the use case. A value around 64 millimeters will produce images closest to human vision, since that's how far apart our eyes tend to be. But smaller values can be great, especially when shooting close-up scenes, and really large baselines are used to capture depth in faraway objects, like for stereo landscape photography. The trade-off with wide baselines is a miniaturization effect, due to the exaggerated sense of depth. For this example, I'll stick to a 64mm baseline. The next piece of metadata, the field of view, is the horizontal angle in degrees captured by each camera. Generally, the higher the field of view, the more immersive, since more of the scene is in view. However, for a fixed sensor, higher fields of view will spread more content across the same number of pixels, so the angular resolution will be lower. Additionally, since our projection is rectilinear, fields of view greater than 90 degrees will be inefficient in their angular sampling densities, especially on the edges, and thus aren't really recommended. For this example, I'm going to use 60 degrees for the field of view. Now, let's check all of our image characteristics. The first guideline states that the images should be stereo-rectified, meaning that the optical axes of the two cameras are parallel, as shown here, and the two images are on the same plane. If the optical axes of the cameras aren't parallel, as shown here, the images will no longer be coplanar, and thus aren't stereo-rectified. If that's the case, you'll have to undistort them with an image processing technique called stereo-rectification. Next, let's make sure that the image centers are aligned with the optical centers. This means that the center pixel of each image is aligned with the optical axis. This is true by default for pinhole cameras, but there's a few subtle ways we can accidentally break this alignment. To see, let's take a closer look at our images. Here's our stereo image pair with an image center that's aligned with the optical axes, but if we crop the images, the center pixel will change. The new center pixel is no longer aligned with the optical axis, and so this cropped stereo pair is suboptimal. Similarly, shifting the images left and right will also change the center pixel and break this guideline. Applying these kinds of horizontal shifts is a common practice in 3D filmmaking to achieve artistic effect, but it isn't recommended for spatial media. To achieve those effects, we have the disparity adjustment metadata, which we'll come back to later. First, let's make sure we have no vertical disparity. The easiest way to do this is to take your left and right images and identify a feature point common to both images. Here, the beak of the bird, and draw a line between them. If that line is perfectly horizontal, then the images are correctly aligned, with no vertical disparity. Here's a different stereo pair, where the cameras were misaligned. We can check for vertical disparity by marking out feature points and connecting them. Here, the line between the feature points isn't perfectly horizontal. This means that the images have vertical disparity and will be uncomfortable to view in Vision Pro. Let's review what we've done so far. We've got our left and right frames that we've ensured are rectilinear, stereo-rectified, optical axis aligned, and have no vertical disparity. We also know our baseline and field of view. Now, let's see how this content gets rendered. That's where the magic happens, and where all of this careful camera calibration will finally pay off. With the information provided, the renderer can construct a camera model that defines how objects in the world were captured by the cameras. Those rays are then traced out in reverse to render two images at the correct size and distance. When viewed in Vision Pro, one image is displayed to each of the viewer's eyes. Their visual system fuses those two images into a 3D scene and perceives a 3D object. When the files are constructed correctly, with accurate metadata and ensuring all the image characteristics guidelines are met, the perceived image that your eyes see will exactly match the real object that the cameras saw. You're effectively teleported back to that moment, replacing the cameras with your eyes. This is what creates that magical feeling of reliving a moment in first person. Our spatial photo can be equally powerful in the shared space. In this mode, visionOS displays these images in a window, scaling down the scene while still rendering it stereoscopically. The goal here is not to be perfectly true to life, but rather to provide an artistically and emotionally resonant 3D effect. To make sure people are comfortable viewing content in a window, we introduce the last piece of spatial metadata, the disparity adjustment. If you're familiar with stereo photography, the disparity adjustment is a hint to the renderer on where to place the zero parallax plane. It's sometimes called the convergence adjustment, or a horizontal image translation. Really, it just represents a horizontal offset, encoded as a percentage of the image width. A negative value will push the left frame to the right and the right frame to the left, and a positive value will push them in the opposite directions. As the images shift horizontally, the 3D scene perceived by your brain will shift in depth along the z-axis. A negative value, therefore, will make content appear closer to the viewer, and a positive value will push it further away. Be careful when setting this value. Too large of a negative value can cause depth conflicts, and too large of a positive value can cause your eyes to diverge, especially for objects in the background, which can be uncomfortable. For this scene, I'm going to pick a value that places the hummingbird just beyond the front of the window. A shift of even a couple percentage points is enough to dramatically alter the perception of the image, so make sure to test in Vision Pro when picking a value for the disparity adjustment. We can now add in our horizontal disparity adjustment, and with that, we have all the inputs we need to construct a spatial asset. All that's left is to package up this data in the appropriate file format: stereo MVHEVC for video, and a stereo HEIC for photos. Our final creation now renders correctly in Apple Vision Pro and looks amazing, in both the windowed presentation and when fully immersive. Let's wrap it up. In this talk, we've learned about the multiple types of stereo media on visionOS: 3D videos, Apple Immersive videos, and spatial photos and videos. We've seen how to capture, detect, and display spatial photos and videos in your apps, and we've discovered how to create your own spatial media with accurate metadata and perfectly aligned images for a great experience in Vision Pro. That's it from me. I can't wait to see all the amazing new experiences you'll build with spatial media.